Primes are the indivisible building blocks of mathematics, but look where they sit on the number line. They appear scattered without a clear rule. When we plot them out, the distances between them, the prime gaps, fluctuate. You have twin primes like 3 and 5 sitting side by side, followed by massive prime deserts where the next prime doesn't appear for hundreds of integers. For centuries, mathematicians searched for a reliable pattern governing these gaps. They wanted to know if the distance between primes was predictable or just noise. Modern sieve methods prove primes appear in dense clusters. But despite breakthroughs, the precise length of an individual gap still looks like random data. We do have a few clear guideposts. For example, every prime larger than 3 is located immediately adjacent to a multiple of 6. But those rules only offer a glimpse. On a flat, straight line, the broader structure is hard to see. To find a precise alignment, we have to move beyond a one-dimensional view and wrap these gaps into a circle. This approach uses a technique called gap normalization. We take the empty space between two primes and bend it until the two ends meet. Consider a prime gap of 12, like the one between 199 and 211. We wrap that distance into a single rotation, so the entire gap equals exactly 360 degrees. There are 11 non-prime numbers inside that gap. We take those 11 interior integers and map them at their exact relative positions along the circle's perimeter. The first integer sits at 1/12 of a rotation, the second at 2/12, or 1/6. This continues around the clock face, giving each a geometric coordinate. By forcing every gap into the same unit circle, the actual length of the gap stops being a distraction. We have a uniform space to see if these integers align with a specific geometric rule. We can test this by drawing fixed rays from the center of the circle to specific fractions on the edge. If we choose a denominator of 4, we look at the rays sitting at the 1/4 and 3/4 marks. Because 4 divides our gap of 12, the integers at 3/12 and 9/12 land exactly on our rays. Every time a denominator divides the total gap, the integers hit these fractional spokes. Now look at a prime gap of 10. 4 does not divide 10, so when we map those interior integers, none of them touch our rays. It's a clean miss. This framework turns the arithmetic of divisibility into a geometric alignment. The specific numbers don't matter, only the relationship between the denominator and the gap size. This isn't just for small examples. We can run this process for hundreds of thousands of gaps, tracking every ray hit across the first 10 million primes. To organize these hits, we use Möbius inversion, a mathematical tool that acts as a decoder to tally the total intensity at every denominator. This matrix shows the result. Each color-coded point represents the coherence between different primes. Because the system tracks exact divisibility, the data is lossless. It preserves the full arithmetic structure of the gaps. The total collection of these geometric hits allows us to work backward and perfectly reconstruct the exact frequency of every prime gap found in the data. This geometric system provides a new way to apply established theorems. For example, James Maynard proved that certain patterns of consecutive primes must occur with a specific minimum frequency. Because our geometric rays correspond exactly to the divisibility rules Maynard studied, his theorem guarantees that every fixed ray will be hit infinitely often as we move through the primes. The representation also models the suppression of repeated residue classes. This graph shows that the distribution of gaps modulo 6 follows a predictable spectrum rather than a random one. When we look back at the number line, the distances between primes still appear inconsistent, but the circular representation reveals that this irregularity is governed by a rigid arithmetic logic. By bending the number line, we find that the gaps between primes align with the same predictable rules that govern all integers.